Okay, so welcome back friends. So in last two videos we have seen Leibniz linear differential equation. So in today's video we will focus on Bernoulli's equation. So Jacob Bernoulli was a Swiss mathematician and he was known for his famous work in probability and elastic theory. So this is the famous Bernoulli's equation. So you can see dy by dx plus px into y, where p is a function of x, is equal to q as a function of x into y to the power of n. So we have already seen how to solve the Leibniz linear differential equation. For example, this is the standard form of the Leibniz differential equation. So here the main problem is that you are having this extra term, that is y to the power of n. So we will understand how to convert Bernoulli's equation into Leibniz linear equation. Okay, so now we will understand how we will convert this Bernoulli's equation into our linear differential equation, that is Leibniz form of linear differential equation, for which we already have our ready-made formula of answer, that is y into integrating factor is equal to qx into integrating factor plus c, where integrating factor is equal to e to the power of px dx. So now our basic thing is that we have to get rid of this y term in the qx term, because we want to keep our qx term independent here. So we will divide the entire equation by y to the power of n. So you will get y 1 by y to the power of n dy by dx plus px y to the power of 1 by 1 minus n, and here you have got qx. So our first step is done. So second step, we want to get rid of y term over here. So we will assume y to the power of 1 minus n as t. So what is the benefit of this? We will see. So now differentiating both sides. So on the left hand side, differentiating with respect to dy, you can simply differentiate this, and you have to multiply by dy also, because this we are using the chain rule. And on the right hand side you will write dt. So we know that whenever we differentiate x to the power of n with respect to dx, we get x n into x to the power of n minus 1. So now applying this formula here, you can write power is 1 minus n y to the power of 1 minus n minus 1 dy is equal to dt. So 1 minus n, here this minus 1 will get cancelled from this one, y to the power of minus n dy is equal to dt. Now let's divide both the side with dx, both left hand side and right hand side. So rewriting it again, 1 minus n 1 by y to the power of n dy by dx is equal to dt by dx. So finally 1 by y to the power of n dy by dx can be written as 1 by 1 minus n dt by dx. So we have actually brought this term on the right hand side. So we will substitute this. Now we will substitute this term in our equation. So here in place of 1 by y to the power of n dy by dx, you can write as 1 minus 1 by 1 minus n dt by dx. Then the second term is pux, and in place of y to the power of 1 minus n, you can write as t. So p as a function of x into t, and the last term was qx. So you can write as qx. So now we will multiply the entire equation with 1 minus n. So you will get dt by dx plus px 1 minus n t is equal to qx 1 minus n. So now this is our final form of Leibniz differential equation, where our px term has changed a little bit. So this is our new px term, which is a function of x, and this new factor has came here. This is our new qx term. This is also a function of x only. So now applying the solution of Leibniz form that we have derived, so you can write t into integrating factor is equal to integration of qx, and our new qx is qx into 1 minus n. So this factor will come because our new qx is this term dx plus c. So this is our new solution, and our integrating factor is e to the power of integration. Our new px is px into 1 minus n dx. So now you can use this solution and this method actually to solve more problems. So let's solve this problem. So you don't have to take any load, just sit back and watch this problem. Take it as an illustration. So here you can see that, so here you can see this extra y to the power of 6 in the qx term. So we want to convert this into the standard form, that is dy by dx plus px into y is equal to qx. So this is the standard Leibniz linear differential equation, and the solution of which is y into integrating factor is equal to integration of qx into integrating factor plus constant of integration. So where integrating factor is e to the power of px dx. So we have already seen this earlier also. So what we will do here, we will divide this entire equation by y to the power of 6, because we want to get rid of this y to the power of 6 term from our qx term. We want to keep our qx expression only as a function of x. So when you do so, you will get 1 by, so when you do so, you will get 1 by y to the power of 6 dy by dx plus here you will get 1 by y to the power of 5 into 1 by x is equal to x square. So now what I will do is I will assume 1 by y to the power 5 as So now I will assume 1 by y to the power of 5 as t. So when we assume this, we will differentiate both sides. So you will get here, let's differentiate with respect to dy on the left hand side and with respect to dt on the right hand side. So here using the chain rule, d by dy y to the power of minus 5, and you have to multiply with dy also because we are using chain rule, and on the right hand side it is dt. So we can use our formula that we have seen, where is differentiation of dx to the power of n with respect to x is n into x to the power of n minus 1. So this here you will get minus 5 y to the power of minus 5 minus 1 into dy is equal to dt. So you will get minus 5 y to the power of minus 6 dy is equal to dt. Now what we will do is we will divide by dx on both sides of the equation. Now in place of 1 by y to the power of 6 dy by dx, you can simply write as minus 1 by 5 dt by dx in our equation. So here you can see in place of 1 by y to the power of 6 dy by dx, you can write as minus 1 by 5 dt by dx plus, now in place of 1 by y to the power of 5 you can write as t. So you will get t here and t multiplied by 1 by x. So 1 by x, and on the right hand side you have x square. So you can see that now your equation is turned into Leibniz linear differential equation form. So just multiply by -5 on both sides. So you will get dt by dx plus -5 times 1 by x into t is equal to -5x square. So this expression, this is your px expression and this is your qx expression. So now you can simply write the solution because we have already derived the formula for the Leibniz linear differential equation. So first let's find the integrating factor. So integrating factor will be e to the power of integration. Px term is -5 by x dx. We have to integrate this. So you will get e to the power of -5 will come outside, integration of 1 by x into dx. So we know that our integration of 1 by x with respect to dx is log base e x, that is ln x. So you can write simply over here e to the power of -5 ln x. Now let's take this -5 inside. So we know that whenever ln x to the power of n actually becomes n times ln x. So this power that is here inside will come outside and it can also go inside also. So when this -5 will go inside, it will give you e to the power of ln x to the power of -5. And we know that as a property of log that e to the power of log e a is equal to a. So actually don't confuse with this. Actually log e is nothing but ln a only. So if e to the power of ln a, you can write it as a. So this is simple log property that you should know. So don't just think too much. So use the log property, or if you are not familiar with the log property, you should revise your logarithmic chapter. So here you can write as x to the power of -5. So finally your integrating factor of is 1 by x to the power of 5. So now what we will do is we will find the final solution. So our final solution will be y into, sorry, y not here, our final solution will be t, because our equation is in terms of t. So we will write t into integrating factor is 1 by x to the power of 5, then integration we will multiply qx into integrating factor. So our qx over here is -5x square. So you can see clearly here qx is -5x square. So -5x square, and we have to multiply by integrating factor, that is 1 by x to the power 5 dx, and finally we will add a constant of integration. So t into 1 by x to the power of 5. So here simply -5 will come outside, and inside we will have x to the power of -3 by solving the exponent part, dx plus c. So we know that the integration of x to the power of n with respect to dx is x to the power of n plus 1 divided by n plus 1. So using this simple formula of integration, we can simply write as dt into 1 by x to the power 5 is equal to -5 x to the power of -3 plus 1 divided by -3 plus 1 plus c. So just let's replace the t term. So what was our t? We have assumed t as 1 by y to the power of 5. So in place of t you can write as 1 by y to the power of 5 into 1 by x to the power of 5. Here again you can write -5 and you will get -1 by 2. So here this will come outside. here you got x to the power of minus 2 plus c. So finally your answer is 1 by x to the power of 5 y to the power of 5 is equal to 5 by 2 1 by x square plus c. So this is your final solution. So let's see one more problem. So you can try this problem by yourself. So you can pause this video and try this problem by yourself. So now let's start the solution part. So here this problem is not exactly of the form of Bernoulli's equation, but it is similar to this. So here also we can see that in our qx term, there is a function of y, which we don't want. So what we will do is we will get rid of this y term, y function initially. So rewriting this equation as dy by dx minus 10y. So in place of 10y, we will write as sin y by cos y. We actually break down the tan y function. Then 1 by 1 plus x is equal to 1 plus x into e to the power of x, then 1 by cos y. So this was actually not so direct question, so it was a challenging question. So let's see the solution. So now we will multiply by cos y to get rid of this y function from qx. So you will get cos y times dy by dx minus, here you will get sin y, then 1 by 1 plus x is equal to 1 plus x e to the power of x. So now your one part is done, that is you have got qx. Now we also want our px term to be independent of y. So what we will do is we will assume sin y as t this time. If you assume sin y as t, so let's differentiate it. So if you differentiate it, you will get cos y dy on left hand side and dt on right hand side. So what we will do, we will divide this by x dx on both sides. Okay, so now you can see that this cos y dy by dx is dt by dx. So you can replace this cos y dy by dx with dt by dx. So let's do it. So you can write as dt by dx, then minus, in place of sin y you can write as t, then 1 by 1 plus x is equal to 1 plus x e to the power of x. So finally you can see that here your px term is minus 1 by 1 plus x and your qx is this term, that is 1 plus x into e to the power of x. So this is your Leibniz linear differential equation. So we know our solution, that is t into integrating factor, then qx into the integrating factor, we integrate it, plus constant of integration. So let's find our integrating factor. So integrating factor will be e to the power of px dx. So what is our px? So this is our px. So you can write as e to the power of integration of minus 1 by 1 plus x dx. So when you integrate 1 by 1 plus x dx, so its integration is ln 1 plus x. So you can just simply revise your integration chapter, because we are not going to make you understand the integration chapter in the present lesson. So here you can write as e to the power of minus ln 1 by 1 plus x. So next step, we will take this minus 1 inside in the power, as we have already discussed in the last problem also. So it will become e to the power of ln 1 plus x to the power of minus 1. And when you have e to the power of ln a, so it becomes a. So this is a simple log property. So here you will get 1 plus x to the power of minus 1 using this log property. So this is 1 by 1 plus x. So this is the integrating factor. So now we will write our solution. So our solution is t into integrating factor. So t into our integrating factor is 1 by 1 plus x, then integration of qx. So what is our qx? this is our qx, 1 plus x into ex, and we multiply this by our integrating factor. So our integrating factor is 1 by 1 plus x times dx plus constant of integration. So you can see that here 1 by 1 plus x will get cancelled by 1 plus x. So, and the integration of ex dx is simple ex only, and constant of integration is c. In the left hand side you can replace this t with the substitution we have seen earlier. So we have seen sine y was equal to t, so you can write sine y in place of t into 1 by 1 plus x. So this is your final solution. So I hope that you have enjoyed the video. So thank you.